We're classifying 4 acids using 2 criteria: concentration and acid strength. Remember, concentration tells us how many moles are dissolved, while strength refers to how completely an acid ionizes in water. Generally, concentrations below 1 m are dilute, above 1 m are concentrated. Strong acids like HNO3 and H2SO completely dissociate, while weak acids like acetic acid and HF only partially dissociate. You'll need to consider both properties for each acid to give a complete classification. We're moving into section 14.2, where we'll explore the fundamental theories that define acids and bases. You'll learn about 3 major frameworks: Arrhenius, Brønsted-Lowry, and Lewis theories, each providing a different lens for understanding how acids and bases behave. These aren't competing ideas, rather, they build on each other, with each theory expanding what we can explain about acidic and basic substances. Understanding these theories is crucial because they help us predict chemical reactions and understand pH, buffers, and countless industrial processes. Here are your 2 main learning targets for section 14.2. First, you'll compare how Brønsted-Lowry theory expands on Arrhenius theory. Notice the key difference is that Brønsted-Lowry focuses on proton transfer rather than just H-ion or OH-ion production, which lets us explain more reactions. Second, you'll learn that monoprotic acids donate 1 proton per molecule, like HCl, while polyprotic acids donate multiple protons, like H2SO4. This distinction matters because polyprotic acids react in stages. By the end of this section, you'll understand both frameworks and how to classify different acids. Now we're shifting focus to bases. You already know acids from our learning targets, so here's what's new. Arrhenius bases produce OH ions in solution. Think of NaOH dissolving in water. But Brønsted-Lowry bases work differently. They accept protons, which is much broader. For example, ammonia NH3 is a Brønsted-Lowry base because it can grab a proton to become NH-, even though it doesn't have any OH ions. This expansion lets us identify bases in many more reactions. Your second criterion reminds you to keep sharp on identifying how many protons an acid can donate. That distinction between monoprotic and polyprotic will matter when we solve problems. Now let's look at the Brønsted-Lowry framework in action. Notice that Arrhenius acids are a subset. They're all Brønsted-Lowry acids too, but the Brønsted-Lowry definition is broader. In this example with HCl and ammonia, you can see the actual proton transfer happening. HCl gives up its hydrogen ion to ammonia, making HCl the acid and ammonia the base. This proton transfer perspective helps us recognize acid-base reactions that don't involve hydroxide ions at all. The key is identifying who's giving and who's receiving the proton. Now we're distinguishing between 2 important acid categories based on how many protons they can release. A monoprotic acid like HCl releases just 1 hydrogen ion, so it's finished after 1 ionization step. But polyprotic acids like sulfuric acid can keep giving up protons in multiple steps. Notice how each step produces fewer ions than the one before. The first ionization happens most completely because the acid is strongest at that point. As you remove protons, what's left becomes a weaker acid, so subsequent ionizations don't go as far. This explains why polyprotic acids behave differently in different pH ranges. Now let's focus on diprotic acids, like sulfuric acid. Notice it has 2 ionization equations. That's the key difference from what we covered before. In the first step, H2SO4 releases 1 proton completely, forming HSO-. But here's what's new. The second step is reversible, shown with the double arrow. The hydrogen sulfate ion doesn't fully give up its second proton. It's in equilibrium. This incomplete second ionization is crucial because HSO4- is a much weaker acid than the original H2SO4. So when we calculate pH for diprotic acids, we can't ignore this equilibrium. We have to account for both steps, but recognize that only the first ionization contributes significantly to the hydrogen ion concentration in most cases. These are the learning goals for this section. First, we're going to compare 2 different ways of defining acids and bases, the older Arrhenius model versus the more modern Brønsted-Lowry model. They have different perspectives on what makes something acidic or basic. Second, we need to distinguish between monoprotic acids, which donate only one proton like hydrochloric acid, and polyprotic acids like sulfuric acid that can donate multiple protons. Understanding this distinction is essential because it affects how we predict ionization behavior and calculate pH. This slide restates your two main learning objectives for this section in a success criteria format. These are the skills you need to master by the end. First, you'll need to distinguish between how Arrhenius defined bases as substances producing hydroxide ions versus how Bronsted-Lowry expanded that definition to include proton acceptors more broadly. Second, you'll practice identifying acids by looking at their chemical formulas and determining whether they can donate one proton or multiple protons. These criteria will guide what we cover next.